Euclid's Elements, Book 2, Proposition 4. If a straight line be cut at random, the square on the whole will be equal to the squares on each of the segments plus twice the rectangle contained by the segments. So start with our straight line, call it AB, and we'll cut it at random at C. And what we're going to show is that the square on AB is equal to the square on AC plus the square on CB plus twice the rectangle, or twice the rectangle contained, or the rectangles contained by the segments. So A, C, CB. And the first thing he does is he builds a square using proposition 46. He builds a square on line AB. So we make square AB. And then call that D, call that E. He joins B to D. And from C, he draws a line parallel to either AD or BE. We'll call that CF. And we know we can draw that line parallel because of proposition 31 of book 1. CF is parallel to AD. And we'll call this point H. He uses prop 31 again, and we draw through H line, call that T and R. TR parallel to either DE or AB. So next step, he uses, I use red here to highlight them. He uses proposition 29 of book 1, which states that when you have two parallel lines cut by a transversal, the exterior angle is equal to the interior and opposite angle, or in our orange textbook, the corresponding angles are equal. So we've got TR, line TR and DE cut by transversal DH or DB, and we've got, well, DB, and then we can say that that angle there is equal to that angle there. Angle TDH equal to angle CHB. And then he utilizes proposition 5 of book 1, which states that in isosceles triangles, the base angles are equal. We know that the triangle DAB is isosceles because the side DA is equal to the side AB, because the whole figure ADEB is a square, which means that this angle here, CBH, is equal to the angle TDH, equals angle, I'll just say ABD. And next, he goes on to utilize prop 6 of book 1, which says that when you have in a triangle, namely the triangle here is HCB, when you have the base angles equal, then the sides subtending those base angles must be equal. Therefore, we can say that side CH is equal to side CB. Now, if we look at the figure CR, we know that it's a parallelogram. because TR, which HR is a part, and CB, which is a part of AB, are parallel, and then likewise we drew CH or CF parallel to BE. Now we can utilize proposition 34 of book 1, which states two things, which we'll use both of those. First one being that the opposite sides of a parallelogram are equal. And therefore, CB is equal to HR, and CH is equal to BR. And they'd all be equal to each other because CB was shown to be equal to CH in our step 6 by proposition 6. Therefore, we'll write up that CB equals BR equals RH equals HC. Now our goal is to get the figure CR to be a square, which means that it has to be equilateral and equiangular, with each of the angles being a right angle. We've just shown that it's equilateral, and now we're going to go on to show that it is equiangular with each of the angles being a right. And he goes back, uses a combination of Prop 34 and Proposition 29 from book 1. First he uses Prop 29. We can see that this angle here is a right angle because it's the angle CBR is right because it's the angle of a square. And we know that the angle CBR plus BCH, together they are same side interior angles. So by proposition 29, they must equal two right angles. And because CBR equals a right angle, well then BCH must also equal a right angle. Prop 29 says that angle HCB and the angle CBR equal two right angles. But CBR, like I just said, is a right angle, and therefore HCB must also be a right angle. And now he goes on to show that via Prop 34, we know that opposite angles in a parallelogram are equal, and therefore the opposite angle to HCR is the angle BRH. So that is a right angle. And the opposite angle to CBR is CHR. So that angle is a right. I think I'm just going to say here in this step that all the angles are right. All angles are right. And now we have shown that the figure CR is a square because it's equilateral and it's equiangular with all of its angles being right angles. And the figure CR is the square built on CB. So referring back up to here, we'll talk about that a little later. But I'll just write that down here, that the figure CR equals the square CB. Step 10, he says, similarly, the figure TF can be shown to be a square. And since TH is equal to AC, then the figure TF is effectively the square on AC. Similarly, TF equals a square, and since TH is equal to AC, therefore TF equals the square on AC, which again is this over here. So we've got this, and this now. We've got those two parts. Now we want to show that we've got this business of twice the rectangles. we'll go to step 12 up here, and we can see that the complements AH and EH must be equal, and that is proposition 43 of book 1. We can say that AH, the rectangle, is equal to the rectangle HE. But AH is nothing more than the rectangle contained by ACCB, the segments of the original straight line, because CH is equal to CB because they're the sides of the same square. Therefore, I can write down here that AH is effectively the rectangle AC, ACCB, but since it's equal to HE, we can say that HE is effectively AC, the rectangle AC, CB. So you take two of these together, but now we've got twice the rectangles. Now, basically we can look and say that look, AH is this complement, HE is this complement, and they take up those portions of the figure. CR is the square on CB, and TF is the square on AC, but those four figures comprise the whole square AE, or the whole figure AE. And the whole figure AE is the square on AB. I'll write this up. Basically, AH, figure AH, plus the figure, or the square CR, plus the figure HE, plus the square TF, all equal the whole figure AE. Step out of the way here. So those four parts equal the whole, but AE, the figure AE, equals the square on AB. And therefore, we've shown that all those four parts, we've shown that it was equal to CB down here. We've got a square CB, we've got the square AC, we've got twice the rectangles here, and they're equal to the square on AB in the last step, thus being what was required to prove QED.